All right, welcome back, everyone. So our next speaker is Jiajun Wu from Stanford, and he's going to tell us about understanding the visual world through naturally supervised code. So the floor is yours.
Okay, thanks for the introduction, Armando. Nice to be here. So I think I'm going to talk about something that's kind of more different. So this is the neuro-symbolic summer school. So when I got it, I was like, what does it really mean by neuro-symbolic? Of course, we have so just to be safe, we have a narrow definition of what is neuro-symbolic. So that's what I'm going to talk about here, which is more symbolic. But I've learned in the past 2 days, especially from Isong, that the interpretation of neuro-symbolic can be much broader. And I could have totally changed the talk to a different talk, but that's okay. Maybe in the future, we have other opportunities to talk about those stuff. Okay, so this is maybe more symbolic, which is nice. So we call it understand the visual world through naturally supervised code. So there's the visual part, which is the program. NSF program is called understand the world through code. So, but we want to see how that can be applied to computer vision, right? So in some sense, you see code or structures everywhere. If you look at, I would say, like the walls here or the windows, right? They're sort of exactly repeating themselves, right? Look at the rails and everything. So there are clearly some, I would say, symbolic structures. And if you look at the desk in front of you, has this kind of rectangular shape. But why is that? If you look at all these chairs, they are identical to each other. So clearly you have notion that there are things that are repeating themselves, they're symbolic. And often they're not really explicitly considered or even implicitly considered in visual understanding systems. So we want to see how that can be put together. Okay, to motivate that, there is rich structure in the visual world. The lights are repeating themselves. If you're in a corridor, if you look at a building, then the windows are repeating themselves. So there are notion of things like planes and symmetry, reflectional symmetry, rotational symmetry. There are cases like repetitions, right? So these are very rich structures. And why are they there? Because we humans build those buildings and corridors, and in this fabrication process, even if if you look at the natural world, it's kind of funny that there's almost nothing that is perfectly symmetric. Now, can you find a perfect sphere in the world? You probably cannot find it. Maybe the only exception is the moon. But other than that, there's nothing that's perfectly spherical. But humans just have this kind of prior and preference that we love these things, and when we're making these buildings, we try to put them together to make them regular. So now the question is it possible for us to leverage these kind of structural information for scene understanding and editing as well? So here's a demo of what we want to achieve. Actually, we put it into this Photoshop GUI, but the underlying algorithm is ours. So this is like what we want to do. First you do interactive segmentation. You have a building like this. Yeah, there's a bounding box and you segment it. And then you can compute vanishing point in 3D, right? These are all kind of standard. But now I say, if I really have a structural understanding or a smart understanding of the building, I want to make the building taller, or I want to make the building wider, then you can just do it in one shot, right? So you have to understand a lot of things here. You have to understand, what is the texture of the building, but you also have to understand there's 3D, there's perspective projection. To make it taller, it has to have the same orientation. But also you understand things like there are a number of levels and there are windows repeating themselves. So you make it taller, you still want the windows to repeat themselves. So this is what I want to do. And all this was like inspired by this earlier work, not that early, but I think probably discussed a few times maybe in the previous sessions of this summer school. That is, there has been earlier attempts by Kevin Ellis with others, including Armando, using program synthesis for visual data, right? So if you give simple line joins like this, and you're right, there's some structures there, but how can I explain it? So the raw input here is always we call it rasterized. You just have pixels, but then you can say let's vectorize it, right? So turning like a PNG into a PDF situation where you want to get, okay, what are the primitives here? There are lines and rectangles. So you can do that by a combination of learning and search. And once you vectorize the image, you have in the collection of primitives, you're now I'm working in this kind of much lower dimensional space and everything is discrete. So we can apply, again, existing program synthesis methods all combined with learning, augmented with learning, to search for a program that explains those kind of primitive shapes, which in turn explain all the raw pixels here. And once you have the program recognition there, you can say, now I can easily do things that which are not very straightforward to do with purely learning-based methods, including extrapolation. Right? So you can make the pattern wider or broader, stuff like that. So all these are pretty nice in 2D, and we actually later had an extension about how to make that into 3D, in the sense that you not only work with lines and rectangles, but now we work with things like spheres and cylinders. But if we want to generalize that into natural images, right, the world we live in, then we have this challenge that is the world is not made of lines and rectangles or triangles or spheres, right? So actually, as I said, there are almost no perfect spheres in the world. So how can we really generalize to natural images like this, where there's a ball with milk and cereal, and clearly there are repetitive patterns here, and you want to capture that. But how do I define, right? You cannot really say the world is made of lines and rectangles. I detect all the rectangles because what are the primitive shapes here? It is not really clearly defined. So we look into this classic idea, interesting idea in computer vision called internal learning or learning from single images. Now, sort of, in some sense, it gets a bit more popular these days because all those single scene optimization methods like NERF and stuff. But there has been an old idea has been envisioned for more than a decade, where you can look at internal statistics about what's going on in the image. And you realize just looking at a single image, there are a lot of information there, right? You find there are all these patches, they're repeating themselves. Such kind of repetition can happen at the same scale, or it can happen across different scales. So why is that? It's because these things essentially they're the same thing, right? So these are like natural graphs, but for chairs it's the same. But then the more in 3D, you take a picture, so there's perspective projection, they got projecting to 2D. So things that are closer to you, of course, they're larger. Things that are further away from you, they're smaller, but they're essentially the same thing. So that's why they're repeating themselves, right? So people have thought about, okay, I have so many signals within a single image. Can I actually leverage these kind of things to learn some, what makes an image, right? What is the image prior, right? Not for the black holes, but for even natural images. So in 2017, basically the same group, they sort of, okay, can we combine that with deep learning in the sense that once you have an image like this, right? So, okay, there are some repetitive patterns. Can I discover that? So they did something that's really simple. That is to look at activation maps. Say this is an image activation patterns. You look at this in like count one or count two features. And then you try to find the displacement on the x and y axis, so that these feature maps, they're most likely to be the same, the correlation is maximized. Right. So you're saying, okay, if I shift all these feature maps by horizontally by x pixels and vertically by y pixels, then okay, these feature maps are most likely to be correlated. Right. So then you do an argmax and you find, okay, this is the displacement between these objects, and you can actually automatically discover, right, what are the centroids of these repeating objects. So why do you want to use the deep network activation instead of raw pixels? Well, I guess technically you're saying these image interpretation neural networks are supposed to be robust to low level features because pixels are really annoying to work with. So there are like different occlusions or lighting conditions and noises. So hopefully the deep level features are trained to be slightly more robust to this kind of environment, to these changes, so that you can more robustly discover the centroids of these repeating objects. So we adopted this idea. Of course, we made some changes to it. Then we are able to discover the centroids of these repeating objects, but now everything's from a single image, right? So there's no prior knowledge that technically it should work on general scenes. Last night we were talking about, oh, maybe we can try these kind of things on the pictures of everyone here in the summer school. And in some sense, now you vectorize the natural images, but what is an object itself is still something that's really hard to explain. In practice, we parameterize it with a generative network. But you vectorize the image in the sense that you figure out and find the centroids about objects in the image. And you can search for a program that explains it. Then what you can do is you have an image of these patterns, and there's one of the crosses missing. So I was like, okay, if I want to solve this imaging printing problem, then of course I don't know what exactly is there, but I have this strong prior knowledge that there should be a missing cross there. And the program can tell you, okay, what are the other patches I should look into? Okay, these are the other crosses I should look into because they have this repetitive patterns. You can put them together to just lower level. It can be a recognition network up here, it can be a generative network. And what you can do is you can paint this missing region. You can put a cross there, and it is not like simply copying patches. It's not any of these other patches. But it is smart, I would say, blending of these neighboring patches, which I believe, okay, what should really be there is given to me by the programs, and how I can really fill it in is told to me by the generative neural networks. And of course, you can also do other things like extrapolation, adding another role of the courses, and regularity editing, or maybe I would say it called as a deviation magnification. Because the world is not perfect, right? So essentially they actually deviate from the perfect rectangular grid. But you can identify those deviations, you can magnify it, which actually has some applications in detecting defects in industrial production as well. Okay, you can going back to the serial example, you can do the same thing where you can in paint a missing serial, you can add another column of serial, you can magnify the deviations to regularity adding serials as well. So all this is about a single plane, and everything you're looking at from a top-down view. So if you're going back to this corridor example, there are things you have to fix. Right? For example, you see all these planes in an angle, right? There's nothing is like really upright, and also there are multiple planes, right? So the question is it possible for us to generalize from a single plane to a multiple plane? We actually turn out we can do that, right? So here you may want to think a little bit more about the structured generation model. If you remember what Vikash talked about last night about this, having a progressive program for the scenes, sort of there's a little bit of connection here. Although here the program is not probabilistic, and also we're not really building a structured generation model for the entire scene, which is kind of hard. But we just want to explain what's going on in these kind of planes. So you have to identify camera parameters, and then you have to partition the scene into multiple planes. And for every plane, you have to search for the orientations of the plane, which is the surface normals and positions. And then you can essentially do similar things about identifying. Once you search for and get the correct surface normals and orientation of the plane, you can rectify it so that you can, in some sense, turn this kind of standard image into our top-down view. So that you can apply exactly the same thing, that is searching for repetitive objects and finding a program that explains it. Okay, but this problem, of course, now you have multiple planes and things are sort of in 3D, so it's kind of getting much harder. In 2D, we're like, okay, we have lines and rectangles, and now going to natural images, we have repetitive objects. But what about this case in 3D, right? So what are the cues, bottom-up visual cues that we can leverage? So we use two things. One is a vanishing point, right? You try to estimate the vanishing point of these planes. And the second is wireframes. Here we use the 2D wireframes. So you see these are line joints. We can also do it in 3D, but turn out the 3D wireframe estimation is not very robust. So 2D is much better, but it also gives you a lot of signals that are not very useful in something like noises, right? Because clearly wireframes here give you a lot of information about what the planes are, but okay, I cannot really see my mouse here. So I should do this. Okay, here, right? So you get all these correct signals about, okay, these are the lines and partition of planes, but also you have additional noises, right? So these are like rails and stuff like that, which are not really indicative of what the planes are. But still I can draw an analogy here. That is, what are the bottom-up visual cues? Essentially, you want to turn this very high-dimensional, noisy visual image into something that's more structured, lower dimensional, and with the hope that then program synthesis algorithms can work better here. So in the case of line joints, that is lines and shapes, right? What are the primitive shapes? In the case of single plane images, we're like discovering repetitive objects. In the case of multiple images, we are using these kind of cues about vanishing points and wireframes. But again, in 3D, this problem is much harder. So just giving you wireframes is so noisy, so it's not enough. Even with all this bottom-up visual information, it's not clear to me how can I really find the right program. So we have additional insight here. That is, based on the vanishing point and based on wireframes, we can generate a number of different possible explanations, right, about how to partition a plane into walls and ceilings and floors. So which one is correct? Which one is better? We humans know clearly that okay, the second one is better and it's correct because we have this prior knowledge about the semantics of the scenes. Right? What does the wall look like? What does the floor look like? But the machines, especially when it's learning from a single image, there's no chance you can have such kind of knowledge. Right? And if you like all these things are pretty reasonable, especially number 3, because it's also symmetric. So how to address that ambiguity? So it turns out that the insight here is these kind of top-down program synthesis and low-level bottom-up visual feature extraction can really help each other. So the intuition here is, it's not only like I'm going to go all the way from bottom up, I extract those repetitive features or training information like wireframes, and I search for a program on top of it. It's also at the same time, only if, you can think about it, only if I can get my plane partition is correct, then my program will actually really help the problem of program synthesis. because it's much easier to explain a correct plane than explaining an incorrect. Oh, that is actually not symmetric. Anyway, to explain something that is non-regular, you have to search for a much more complex program. And explanation, the reconstruction performance will be much worse, right? So anything that is in the correct partition actually makes the program synthesis a lot easier. So you can actually leverage the fact that the program synthesis algorithm works better, or the synthesized program is simpler, as a signal to help your bottom-up visual recognition problems. So let's say we have all the three candidates. I don't know which one to choose, but I can say, okay, let's just assume each of them is good, and then let's proceed. And you can find all these different partitions, and you can search for or estimate the surface novels of these planes, and you can rectify them. So you can rectify each plane. This is how the rectification, after the rectification, how the rectified planes look like. You realize that with the correct plane partition, the rectified planes look much more regular, and a program representation will be explain these correct planes much better compared with these incorrect plane partitions. So the top-down program synthesis also gives you signals about how you can do better on bottom-up visual cue extraction. Yeah, so these things should really be considered together. Actually, there's some part I skipped. That is when you're estimating orientation of the plane, which is like the orientation, the surface knob of the plane. There's also a little bit there. That is plane estimation, rectification, and program synthesis also help each other. So you should really think about it as a holistic optimization procedure. And then you can get the right plane partition and the correct programs. You can explain that. And what you can do with this kind of structural representation is now you can move forward. And so you can do not only like one step or two step visual synthesis, so you can really go a long time and see what's going on there. And you expect the slide to become larger and compare with baseline to everything end-to-end in pixels, then we can do much better. And we don't have this kind of distribution shift issue in the long term. So it's not going to become blurry. But of course, just to be completely fair, right, we have the assumption that the world is a box or something, there are multiple planes, while the baselines don't have such kind of assumption. So they probably work better, they definitely work better actually on data without those kind of constraints. But when we do have some structural priors about what a scene looks like, you can do much better than those kind of unconstrained end-to-end baselines. What else can you do is if I say I want to look to the up left, right? So what's going on there, right? You will expect there's another line coming in, while the baselines cannot really do that. Generally, sometimes it's smooth and blurry. But you should expect there's another line coming in. If you want to look to the top left, or if you want to go backwards, again, you should expect the lights keep coming in, and then the shadows on the walls, they should repeat themselves as well, instead of just making see a bit smaller. And as well as if I want to look backward, right, what will happen there? Even just with a single image, I have no signals about what's going on in the back. If I have to pick one explanation among infinitely possible explanations, I would say maybe there's an infinite corridor. So going from a single image, I would say, yeah, the back should also be a corridor where the lights just keep repeating themselves. There's of course no infinite corridor in the world, but there's one that is approximately infinite at MIT. So the project was inspired there. That is, MIT has this very long infinite corridor. So I was like walking the corridor, going from single image can actually synthesize the entire scene. So this is what we can do, right? Going from the single image, you can actually synthesize the infinite corridor by leveraging those kind of programmatic structures with deep generative networks. And seeing a corridor is like you're in a box, you have multiple planes, but you're inside a box. So if you think about it about a building, then it's essentially the same box, but you're seeing it from outside. The only difference is now you have two vanishing points instead of one. But essentially the messages are similar. If you compare with the baselines, which try to make the building harder, some of them do things realistically, but they don't really abstract the input. Some of them, just don't understand 3D or something. So our method can do much better. Yeah, so this is drawing work with Jiajun Wu, who is now a PhD student at MIT. This is also back when I was a PhD student at MIT, a little bit, and also when I was at Google. And Ikali is a PhD student at Stanford. Okay, so we talked about going from visual program synthesis, line drawings, to single image learning. Now you work on natural images, and going from a single plane to multiple planes. Now you work on these more complicated scenes. So what is next? So in some sense, you can say the first two things are like sort of like 2D, and I wouldn't say the last case is 3D because you're not really testing over 3D structures. All you know is there are a number of planes and they have some surface novels. So maybe we can call it like a 2.5D, right? So it's kind of a surface representation. So of course, naturally, you want to say, what about we go to 3D, right? Especially if you look at those man-made objects again, these shapes, right? Especially like tables, humans made them. So because of our preference or biases, whatever, during the fabrication process, we introduce the priors from humans. We make those shapes to be regular, have those kind of abstract and program-like structures. So it's kind of very natural, right? Think about, in CAD modeling, all those stuff, that you want to explain them with a shape representation. And it's not, of course, not surprising that in computer graphics, a lot of people have explored that. There are things like L systems where just with two very simple rules and very compact grammars, you can actually synthesize pretty realistic hierarchical structures for branches. And probabilistic CFG, right, to use averaging symmetry to explain the shapes and to complete the shapes. And there are also other works at MIT where they're like, given the shape, you can actually do this inversion process. This part doesn't have learning, so it's purely based on optimization, right? So you can search for the constructive solid grammar that explain the shapes using optimization. So it works on single scene, but it's kind of slow. But then people are like, can we do something better with learning? That is, if you have a data set. I'm going to be also part of this, right? Yeah, so do the data set with this collaboration with MIT and all of that, where you have to use this kind of action object shape, but you also explain the fabrication process. What are the steps you need to go from the original, to go from raw primitives to the final shape? And once you have the data set, you can probably imagine there's some combination of learning and optimization can be do together. So I don't have time to talk about this paper in detail in our work, but at a very high level, I'm happy to talk more offline. But at a high level, we're like, is it possible to do learning, right? Put learning together to use learning to infer the program-like structure, but also for shapes, right? So, so going from a raw input shape like this, we want to explain and search for a program-like structure that explain the shapes. The department here is kind of hard, and one insight we have here is usually it's kind of complicated to execute a program, especially so there are several opportunities, right? One is you synthesize a lot of synthetic data and you do supervised learning, and the other is if you want to do self-supervised learning, because the challenge here, or in general, right, for anything about visual program, why do we need single image learning, or why do we need these kind of neural representations? Partly because it's very hard to get annotations for these kind of shapes. We have this Fusion 360 gallery, which is nice, but still, right, it's kind of a fixed set of objects. If I give you new objects, how would you get annotation of that? How would you generalize? So of course, you want to do it in a more self-supervised way. So one thing we thought about is, okay, if we can make the program executor differentiable, right? So that would be great. We've learned a lot of approximate techniques to make them differentiable for program execution, which is very nice. And back then we're like, what if we just make the program executor also a neural network, right? So then, of course, then it becomes differentiable, and you can put it together. In some sense, it's a little bit like execution guided steps using the executor neural executor to guide your search of the tuning of the neural program generator. And if we assume there's a DSL for the shapes, then you're able to get a program for the shapes. And the benefit of that is, if you look at applications like single image shape reconstruction, then which is a popular problem in computer vision. Given a single image, you want to get a shape out of it. Usually, this is what people can get. Right? It looks kind of pretty. This table input is image, output is shape. This is like two different views of output, which looks pretty nice, especially if you look at the input view. Right? So the input view and the input image, they look like almost identical. So which means there's actually very little signal you can get from input image about what shape actually look like. But if you look at the top of the table, then it's kind of reasonable, but it's not perfect because we have this kind of very strong prior that at the top of the table, we probably looks like, it should be like round top, but it's not the case. But you just don't have the signals from the input image. So you have to resort to prior knowledge about, what the shape look like. So in some sense, the prior come from the DSL. And if you map your reconstruction from raw visual space like voxels or meshes or point clouds into program space, then you can do this much better. Okay, so here's a good place to pause, and I think there's a question. That's correct. Yeah, that's a neural network, so it's differentiable. It is trained to execute a program, which means it takes the program and output a shape. It takes the program as a structured representation, which is, what is the program sentence here? And there are a fixed number of program sentences you can represent as one hot vector or something. And they have different parameterizations for each. Yeah.
Follow-up question to that. Program like this, doesn't it already have established semantics? Why do you need to learn to execute?
Okay. So the idea here is is ideally you want to learn it without supervision, in the sense that you can have the program generator like an autoencoder, but the encoder part, and then the executor as the decoder part. So you can do this kind of encoding, decoding, self-supervised learning, which means if I give you a collection of shapes without any program annotations, you can discover these themselves. In practice, it doesn't work that well. But what we can do is we generate a small sample of synthetic data, but then you can use that to pre-train the program generator and executor, but then you can do some, I would say, self-supervised adaptation to much larger shapes that are unannotated, as well as shapes that are from a different object category. So you can adapt to that. Yes.
This is a question basically a couple of slides ago when you were talking about anxiety and how the best partition is the one that allows the program itself to explain what the source program in some sense.
Right.
I'm trying to understand what happens when there are multiple such regular patterns. For example, you showed that image of the callus, the rail thing. And in there were multiple sub-patterns, which you could always identify as the most regular pattern in some sense, which would essentially lead to similar simple programs in some sense. So just wanted to get your thoughts on that.
That is actually not true, because if you look at this example on the right, right? So this looks like a reasonable explanation, but because essentially there's surface and 3D surface normals, and the walls and the floors, they have different surface normals. So if you sort of assume that they're on the same plane, then you have this assumption that is everything on this plane should have the same surface normals. So if you have that assumption and use that to rectify the plane, then what you will get is actually something like this, right? Which is not regular compared with what is actually going on before.
So when I'm talking about, we go back 2 more slides actually, but maybe I can take this off.
Yeah, maybe we take this offline. Yeah.
Yes, okay.
I'll take one more question and I have to proceed. Yes, sir.
A while back there was a famous bug where a copy machine when they're scanning a document, they replace digits with similar looking digits, like the control hatches or similar. So how do you prevent throwing away subtle but useful information?
Not sure I fully get it, but sounds like you're saying, but isn't the case that the deviation magnification case is suggesting that? That is, you can have some regular explanations about what is actually going on in the scene, but it may not perfectly explain what is going on because, let's say you have a shirt and you have a number of colors, but one of them is missing. But you can still search for kind of program representation that explains it. But it will also, because of the the likelihood, if you look at the likelihood function, then there are patches or part of it that it's not really explained that well. But in some sense, that's suggesting a kind of a deviation, which I would say in some sense that's actually a benefit of this program representation because you can identify these deviations and you can magnify it. You can say, okay, this is not perfectly correct. So that part, maybe there are some issues here. So in some sense, going back to a digit example, I would say everything is the same digit, but this particular digit has a lower likelihood, which means it may actually be a different digit. So I can actually, in particular, look into it and magnify the deviations. Is that what you're saying? Sorry, I'm not sure if I fully understand it, but it sounds like that's what you're saying. Thanks. Okay, I think I should proceed because there are a few things that I feel more excited and we can talk about it. Not here. Okay, so we have the program stuff. Okay, but there's this more fundamental question that we have spent all the time thinking about. We have a visual program and how to synchronize that, right? 2D, happy, and 3D. But then there's more fundamental question, that's why the program is even there. So I've hinted a few times, that is the program-like structures, they originate, at least for these human artifacts, right? They originate from human preferences in the fabrication process. So when we made them, when we made this kind of beautiful waves, then we introduced a lot of important priors. So in computer vision, there's this fundamental problem called intrinsic image decomposition. We're given this RGB image, but what is really there is the surface models, which is the shape, below, which is, you can think about as color, material, which is here the reflective surface, this in the material of wall sign was different from material wood, right? So the reflective surface, and then diffuse spectral maps and environment maps, which captures light. Okay, So we always wanted to say, okay, if we can discover these intrinsic images from a raw image, and then we will be able to do a lot of other things like seeing objects from a different view or relighting or something, which I'll show you some demos afterwards. But this problem is, of course, intrinsically ambiguous, right? So you're going from one image to 6 different images. And of course, there's some connections between these things, but how would you even be able to solve this, right? It's like you're having this A times B is 1, but you want to go from 1 to A and B. So to address this ambiguous problem, we thought actually there is some level of, I would say, symbols or code here, but kind of subtle. So this is how I would explain it. That is, when humans, when we try to make it, right, we want to make this space and want to make it look beautiful. So we made it perfectly rotationally symmetric, right? So you actually have a very strong paradox about the surface normals because we want it to be, I would say, symmetric, rotation symmetric here. And what about material? We also know that this whole thing is made of the same material. So although some part of it is brighter than others, we know it's because of lighting. It's not because of other material. So we have some kind of pretty structured and explicit priors about the regularities of the code of the objects. And what about albedo? So the texture of the object, I would say, it is also sort of regular because this thing looks to me like it has the same texture. But here the same is defined in a more subtle way because they're not like pixel level similar. Every 2 pixels, you want albedo maps that are kind of different. But they look to me like perceptually similar. So I would say there's kind of an implicit regularity or implicit code here. That is, we want this thing to have the same texture. And sometimes lighting can have some structures. That's why if you look at the lighting here, there is actually some structures. But let's say in inverse, usually we consider lighting to be unstructured. Okay, so we actually have a little bit of knowledge to solve this ambiguous problem. That is, we have this asymmetry. We have this structured code. That is, some part of it, when we try to make the object, we made it to be more regular, more structured. Some part of it, we made it to be less structured or implicitly structured. Some part of it, we cannot really control the structurality at all. So can we leverage this kind of, I would say, structure or asymmetry to solve this intrinsically ambiguous problem? So we're inspired by this earlier work, which is CVPR 2020 best paper, where they try to do sort of similar things going from a single image of a 2D face to reconstruct the shape. But how would they do it without supervision? Everything is unsupervised. So how would they do it? They discovered that things are reflectional symmetric. So, but what is really reflectional symmetric is that with the shape and albedo, which is action. But the lighting is not symmetric. So what you can do, and viewpoint, the camera viewpoint is not symmetric. So what you can do here is, if you're going from image to these kind of intrinsic images, and you flip the text, right? You flip it horizontally, and you flip albedo, the image should look exactly the same, right? So you don't change the lighting, you only change the depth, you change albedo. The image should look exactly the same. So by leveraging this kind of very minimal code, what they can do is they can go from a single image to this kind of 3D aware shapes, right? You can see going from a 2D image to 3D shapes and stuff like that. So this is not my work. This is earlier work from Jiajun Wu, who was PhD student at BGG from Oxford. But then he did an internship at Google when I was at Google. So we thought, is that possible for us to go beyond symmetry for 3D reconstruction, but more generally leverage structures for image de-rendering? So if you can really go from an image to de-render and get those intrinsic images by leveraging things like structural regularity, then what you can do is you can see objects from different views, again, all from a single image. You can sort of virtualize the scene from different views. And because you have materials and lighting representations, you can also relight objects. Right? So without supervision, all from the single image, you can do none of these things in relighting. So how can we leverage the structure about this kind of explicit or implicit structures there? So we build a system like this. So you're going from an image, and the first step is, yes, there's shape. And we know humans, when we make this maze, we made it to be perfectly rotationally symmetric. So we can actually represent the shapes using this kind of solid revolution representation, right? So you can actually parameterize it with just like essentially like 1D vector. And you can reconstruct the shape, and that can do the first loss, which is the silhouette, right? The surface, the shape loss should look like going to a silhouette. And then you can go through this kind of standard image decomposition pipeline, where once you have the shape, you can unwrap it, right? So just like you can rectify the plane to make it upfront, you can unwrap this kind of base image to make it look like patches, and then you go through this kind of standard image decomposition pipeline. But here you're also leveraging assumption that everything is made of the same material, so you can parameterize the material with these 2 parameters, which is essentially about how it reflects the light, and applies to every pixel on this patch because you know the base is made of the same material. Okay, so these are the material and the shape are the two places you leverage the explicit regularity. You can actually parameterize them with just a few parameters, either two numbers or a vector, a 1D vector. So then you can go back and you get the standard recomposition, I would say re-rendering pipeline, where you can get a few spectral maps, you can put back a middle, you can reconstruct the shape, you can put back, you can wrap it again back to the base, and then you can compute this image reconstruction loss. Okay, these are pretty standard. So what is not being used here is we also said in albedo, right? This thing, it looks kind of the same to me, but it's not like this pixel and that pixel the same. It is more like a perceptual similarity. So can we leverage this kind of perceptual similarity in the sense that when we made a base, we want it to look like uniform, but not like pure color. So how to do that? We introduced two additional losses. One is you can, okay, it should look roughly similar. So if we just compute the mean, and I use the mean to reconstruct the shape, and then this kind of mean albedo reconstruction should also look at the input image, right? So this is kind of easy ways of using it. But if we think about it more fundamentally, about why this thing is so important, why I would say, yeah, this thing is looks the same to me, it's perceptually similar. So what does that mean? I thought that actually means, if you sample patches from it, then I should not be able to tell where the patch is coming from, right? So in some sense, if you think about a case of learning or neural networks, then the perfect realization of that is you can have a discriminator. You can sample patches from it, you can send it to the discriminator, and it should not be able to tell which part of a beetle, which part of a beetle is the patch coming from. So this is actually a very, let me go a little bit deeper here, because this is actually the most fundamental challenge in intrinsic image decomposition. That is, you're going from an image like a base, especially the shiny images. And then there are patches there that, because it's shiny, so there, if you look at RGB pixels, it's like pure white, 255, 255, 255. But then how can you go from this pure white pixel to tell that the vase is actually orange, right? There's no signals there. So what we did here is, if you sample patches from this albedo map, that is what is the true color object, but you sample it from regions with different spectralarities. Some part of it is very shiny, some part is not shiny at all. So then the goal here is no matter which part of the patch I sample albedo from, if I send it to a discriminator, and the discriminator should not be able to tell, if the patches are from a region that is not specular at all, or if the patches is coming from a region that is highly specular, right? Even if the input is pure white, 255, the reconstructed albedo should look like the same perceptually as told by a neural network albedos from other different regions. So in some sense, it's kind of forcing the system to generate the uniform, I would say, implicitly regular albedo maps, which is essentially addressing this kind of I would say the most challenging problem in this whole system. Okay, so put everything together. Again, let me go back to here a bit more. Right? So if you look at the patches here, right, this thing is kind of pure white. And if you unwrap it, this thing is like pure white, almost pure white. So how do we go from this pure white pixel to tell, okay, this is actually the real shape, real color of the object, right? So this is very little signals, but if you're saying, this patch looks similar to this patch, I should not be able to tell this patch is from a highly spectral region. Then it sort of forces images to use a very implicit code to force the neural network to give you something that really, explains the entire generative model, or the generative model is the human fabrication process. And so now what you can do is here are more results. You go from an input image, you can decompose it, you get a surface normals, albedos, diffuse spectral maps, materials, and environment maps. And with that, what you can do is you have now a collection of images, and you can go from them all from a single image. You can virtualize them. You can see them from different views. And you can rely them. Right, so input is just like a single image. And here, more results which are from different data sets. It's more unconstrained and some complex background and stuff like that. So you can do the same thing. Of course, assumptions, whenever you have a prior, you can right, sometimes it's not correct. Like here you have a tag, but we're not assuming there's a tag, which means the tag now is modeled as textures. So it's kind of painted on the image. But allows you to do other things, though, even like going from paintings, right? Going from paintings like this, these are like in a while things. You can virtualize it. You can see it from different views, and you can rely it as well. Okay. Yeah. So we talk about getting 3D shapes, but also discovering. So in some sense, right, it's this fundamental question that we heard a lot of debates already in the past 2 days about to what extent whether inductive bias should be explicit or implicit. It can be fairly explicit. It can also be very implicit in the sense that people may not think it as symbolic. I see it as very symbolic in the sense that you leverage this fundamental inductive bias. Although it's not implemented as a program, it is implemented in the sense that how you parameterize and model different parts of the system. Something I don't have time to talk about is, of course, there's also structures in time, right? You can use it to model human motion, synthesize human motion, but more fundamentally, you can also model it, use it to model things like actions, right? So we have some other works on using linear temporal logic to quantify an action with a combination of LTL and neural networks with applications in task planning and robotics, which is a totally different thread, so I'm not going to talk about it, but happy to chat offline as well. Okay, finally, I have another 15 minutes. So I'm going to talk about something I feel like is important. That is, once you discover all these structures, you not only want to see them and model them and use them, sometimes you want to talk about it, right? You're like, okay, this is a lag, right? This is a lag. So what does it really mean by lag? Right? Can you understand and ground those kind of language abstractions or concepts? And that would be really useful because if I ask you how many lags are there, you want to be able to answer there are 4 lags. But to answer that, you have to understand what it means by lag. And this is lag, that is lag, this is not a lag. And in some sense, you also want to do it without supervision because you don't want to do from a lot of data sets, you say, this part is lag, there's a lag, and stuff like that. So, which is very hard to get those kind of labels, especially in 3D. So it's much more natural to say you have a collection of images, some descriptions, some captions, but can you actually understand those kind of concepts and ground them onto the visual data? So, yeah, finally, I want to talk about this is the final source of natural supervision. So in some sense, part of it is not very natural because this is entirely not from nature or nurture, because humans made it. So the natural supervision is actually from humans. But still, I'm like, where are these code actually originally from, right? They're fundamentally from, if you think about what are the different parts of generative models from humans, from nature, they actually tell us. So another part of the natural supervision is when you have to talk about it, you have to invent a language, you have to communicate. So to communicate what is a lag, you discover these concepts, now can we ground them? Of course, they have a lot of applications, like say, if I ask you what's the color of a fire hydrant, you can answer it, but that requires you to understand what is a fire hydrant, what is the color, and we have to understand what is meant by zebra, and zebras and giraffes are different. To answer it, there are 3 zebras, like there are 4 legs of the chair or something. And you use it for all those different tasks. Once you see a scene like this, you're saying there are color, shapes, and materials, and you can do question answering. Let's say what's the shape of the red object or sphere. You can do captioning, you can talk about it. You can also do instance retrieval, right, which is very important. If it's not a sphere, okay, give me more of a sphere from the data set. Right, so shared between all these tasks is there's this notion of concepts. That is, in a lot of works, they have end-to-end neural network systems that allows you to do this kind of question answering performance really well. But also at the same time, there are 2 things that are done at the same time, but sort of in a tangled way. That is, you're trying to learn concepts, which means the colors and shapes, but I also want to perform things like reasoning, which means how can you count the number of objects, right? You can count the number of red objects in the scene or something. So they're entangled, which means the concept you have learned is kind of a bit hard to transfer if only solve a different problem like instance retrieval or stuff like that. It's not directly clear to me how you can do that. So we have this very earlier work that is, okay, what if we live in a simple world? Again, we're going back to the world where everything is geometric primitives. Then you can say, okay, of course, we can use computer vision to parse the scene into this kind of purely symbolic representations, and we can do semantic parsing of the language. You can get a semantic program of the language and you can execute it. Right, so in the execution part, you don't even have to see the input and language because you already have this very structured symbolic representation. You can answer the question. You can find the right objects and then you can get it censored. But this work clearly had the same problem as the very first work I talked about. That is, we don't live in a world of lines and rectangles or spheres. So again, if I go into natural images, like giraffes or zebras, right? So how can I get annotations for that, right? So it requires concept annotations, what are the attributes and objects in the scenes, as well as it requires program annotations. What does it mean by a question? semantic program, both of which are hard to get, especially in the case of the natural world. Are there animals grazing? It's really hard to annotate these in the natural images. So if you want to do it on natural images, you have to do something that's kind of different. Yeah, we don't have concept annotations. We don't have program annotations. And our thought here is, yes, we don't have each of them, but just like, this is kind of a bit of a loose connection. That is just like you can think about how visual cue extraction and program synthesis can be done at the same time. You can say, can concept learning and program learning be done at the same time, and how they can be done jointly to bootstrap the learning of each other. So let's go back to this simple case so that I can explain to you what's really going on here. That is, you have an image of two objects, you have this question, and then here what we want to do is we want to learn the concepts and do something to learn to understand the question and then to understand the sentence at the same time. So what we're doing here is, we have object detection and there's feature extraction. So you have object-central representations where every object is not represented as a latent vector. And you also do semantic parsing, so you have this program. But then at the same time, because you don't want to assume you understand what rad means, right? Because essentially the goal of the project is to understand concept embedding. So you assume there's a concept embedding for the words like rad as well. And then what the goal is, you can have some neuro-symbolic reasoning module at the end that put together all these symbolic representation for the images, for objects and words, as well as the symbolic program for the question. So you can execute it, you can actually get the answer that is sphere. So when we say we want to do joint learning of concepts and programs, so here the concepts, there are two things, right? That is the concept for the words, what does it mean by rad, and the concept for the visual objects, what does it mean by object one, as well as the program here is the semantic program of the question. So I want to see how they can help each other. So let's look at the first direction, that is how program learning can help concept learning. Once you assume you already understand, okay, the shape of the rad object means, I'm going to find something that is rad, whatever it means, right? And I want to query its shape, whatever it means. So once we understand the program, how can it help me to better understand what is meant by rad and to better learn features of the objects? So what we can do here is let's assume this program is correct. So then I try to have every object, I want to find something that's rad. So the object has its own latent representations. And then you can have this kind of small color projection network that you take this object vectors, and then you can send it to this color projection network, which gives you another embedding, which is hopefully something like the color of the objects. You can do that for every object, but then you can also see, okay, there's a rad embedding. I want to find something as rad, whatever it means. So I can compute the distance between the color of object one and rad and color of object two and rad. And you find that, okay, the distances between color of object one and rad, they're pretty far away. So it's unlikely that object one is rad object. And it's more likely that object two is a rad object. Okay. So now you go to the second step of the program, you inquire its shape. You again take this object vector, go to another projection network and find the shape of the object. And just like you have embeddings for rad, you also have embeddings for possible shapes like cubes, spheres, and cylinders. And yeah, the shape of object two is more unlikely to be a cube, more likely to be a sphere, unlikely to be a cylinder. So again, a lot of things I talk about here is huge approximation compared with what's actually going on in the paper. But happy to talk offline, and you can also look at supplementary material for more details. So this allows you to, the whole execution process can be made approximately differentiable. So you can actually essentially use neural network to approximate the execution process. So every small part is a neural network, and you can see the probability I saw we also saw. So you can allow differentiation, you can pass the gradients. Now you get this very weak signal, that is, I have this program and then execute it based on embeddings or concepts I've learned, I get the answer. So my answer is maybe sphere, or maybe my answer is incorrect, maybe I'll say cube. But you have the supervision at the end, that is what's the correct answer. You can compare your answer with the Rashid's answer, and you can say, okay, if my answer is correct or not. As I said earlier, because the whole process can be made differentiable, so you can actually use back propagation, right, based on the fact that whether you're answering the question correctly or not, to update the embeddings you have learned, the concepts you have learned for the objects and for the words. So this is how program learning can help concept learning. And in the other direction, how concept learning can help program learning. So here we're going to assume that you already have all these concepts, they're hopefully perfect, but I don't understand what this question means. So what's the shape of the rad object? I don't really understand what that means. So I can generate a number of hypotheses. I can say, oh, maybe it means I want to find something that is rad and inquire its shape, which is correct. Or I can have, through search, I can have a number of incorrect hypotheses. That is, okay, maybe that means I want to find something that's rad and see if there's an object that has the same shape. So that is an incorrect interpretation, but I don't know which one is better. But now luckily you have the concepts there. So what you can do is I can try and see, right? So if I execute the first program, and then I can say, okay, is that correct or not? And I will get the answer that's here. Okay, so if I think this is the correct interpretation of the question, then the answer is correct, can come with the wrong choose. So they give me some signal that is, it's not guaranteed, right? So if you're just lucky, you have a different interpretation, but somehow the answer also is here. But at least I give you kind of strong signals that is, this is likely to be the correct interpretation. And if I execute the second interpretation, as I say, a red object, is there anything else has the same shape as a red object? Then the answer will be no. But no is different from sphere, right? So the correct answer is sphere. So by answering no, that gives you a strong, this is deterministic, right? If the answer is incorrect, then definitely this interpretation is incorrect. Okay, so that gives you some signals about which interpretation is more likely to be correct. And because here there's a little search going on, very plausible search, and that is not that differentiable. And so what we did is we used reinforce to guide your learning or parsing of the program. And of course, this part is particularly hard. So not surprisingly, to make this joint learning work, we also have a curriculum that is to go from simple questions, what is the shape of the red object, to slightly more complex questions that involve binary predicates beyond just unary predicates. That is, okay, what is the green cube behind this red sphere? Yes. So here you have to understand behind, and then go back to eventually to complex scenes and complex questions. This is again with Jiajun Wu, who is PhD student at MIT. Okay, so we can do the benefit of this approach is first, we call it neuro-symbolic concept learner. So first, it achieves comparable performance with all these end-to-end neural networks, right? So on the clever data set, also on the real data set as well, at least back then, which I'm going to show later. But it achieves very good performance. It's not really hurting your performance, right? Because there's argument that also sort of hurts your performance, which is sometimes true, and even those program calls, they ask you to see what approaches as long as it doesn't hurt more than 5%, that's okay. But here, at least it doesn't hurt, it almost didn't hurt, right? It's actually improves slightly. But also the benefit is it lets you do much better in the lower data regime. If you have 10% of data, then you can do almost perfectly as 100% data, while these entry approaches needs much more data to make it work. And allows you to do combinatorial generalization. That's a lot of things that all what we care about, right? So you have this training images with simpler objects, fewer objects, and simpler questions. And every method does pretty well on that. But if during testing you have more objects in image and you have more complex questions, then our model still does compare almost the same as the simple images, but the baselines doesn't do as well. And because we're not living in a world of spheres and rectangles, because we have to try to have this object-centric also learned concept representations for every object. So it does work on this general analysis where you can say, okay, what is the fire hydrant, right? You can actually find the fire hydrant and get its color, and as well as answering questions like how many zebras there are. So you can identify the zebras and they're different from giraffes and count them. You can do concept retrievals, like okay, can I find other horses in the images data set, or persons, or compositional concepts, right? Can I find what is mean by on? Because you remember, you learn what is mean by behind, you learn what is mean by on, and person and skateboard. So you retrieve compositional instances, like what are other examples of person on a skateboard. And you can also do the standard task that people often do on these data sets, that is VQA, question answering. So on this entire data set, called VQS, which is for visual question answering, but S is for segments, which means all the questions about things that can be visually grounded, right? Because sometimes they ask about things that are not really visually grounded, and you have to rely on knowledge base. So we cannot do that. But we only care about things that here, these things that can be visually grounded, and actually achieve the comparable performance with entry-end methods as well. Okay, yeah. So that's kind of sort of the last piece of the talk, which is how we can connect that to language and to not only seeing these parts, discover those concepts or abstractions, but also to refer to them, to talk about them, to communicate with them. So in some sense, to summarize, everyone has been talking about, you can use neural networks for recognition or pattern extraction and symbolic representation for generalization. And I think people have also talked about maybe something can be deeper beyond that. But any type of integration, there's this fundamental question that is, which part of it should be symbolic, and where are the things that where the symbolic parts originally come from, right? If you come from something that is, we come up with, like we as programmers or researchers, we say this thing should be symbolic, that thing should be neural. Then it also have this challenge that people may say, yeah, but what if it didn't generalize, right? You have more data, may not apply or stuff like that. So we're like, okay, maybe the symbolic part should be naturally supervised, not coming from us. Sure, coming from us eventually, but not coming from us as a researchers, but coming from how the world is made, right? If the world is, there's 3D to 2D perspective projection, there's light, and this is how graphics engine works. But also, when we're thinking about how these human artifacts are made, so some part of it, yeah, so they're actually, sure, eventually that come from humans, but these are the fundamental generative process. The generative process is a physical fabrication process where these symbolic concepts are introduced. Right? So it's not like I come up with, I'm coding, and I say this thing should be symbolic, that thing should be neural. It's really going back to the very original fabrication process of generative models, and to put those symbols and language as well, because we have to talk about them. So we, in some sense, humans develop this language, and we come up with a word because there's a need to refer to something. So we're like, oh, that is a natural supervision that gives us. So that thing should be, symbolically grounded, right? Visually grounded. The symbols should. So where do symbols come from? Which part of the neuro-symbolic architecture should be symbolic? Or maybe that should be naturally supervised. And so what's next? Of course, we want to make it work on more general scenes. So here's an image from Inception, where you have all these kind of columns, right? They're kind of structured, but there are also a lot of things that are not structured, like background trees and skies and stuff. So can really make it work on more general scenes beyond just like buildings and corridors. At a methodological level, what's the role of symbols and programs? And we have talked a lot about efficient inference algorithms in the summer school as well. And everything here is kind of passive. So can we go from interaction, right? A little bit on interaction about I hinted a little bit. We have been doing something on how you can ground the actions and use it for task planning, but maybe more there, as well as a little bit on language, but essentially that ties to human cognition. So how to make the connections there. So that's it. Thank you.
Yeah, so I have a question about sort of the last paper you're talking about here.
Yes.
You mentioned that you have this sort of like color projection network.
Yeah.
I have two questions about that. First of all, like, am I understanding your approach correctly that you essentially need like a projection network for each type of concept?
All right. So as I said, this is a huge simplification. It's because we try to make it easier to understand. So in practice, on Clever, it does have two projection. Actually has three, because I think one is color, one is material, one is size, one is shape or something. But on natural images, on the VQS data type, for example, there's no way you can have different projection network for different type of attributes. It's not even clearly defined what those type of attributes are. So we just have one neural network, which is called feature network, which takes the objects and project into a feature. And then everything else, like zebras, giraffes, fire hydrant, they live in the same space. Yeah.
Okay, cool. Yeah, that's a great answer. And also, just clarify, that's also training with this distance supervision.
That's right. Yeah, this is the same. Yeah.
Awesome. Cool.
Thank you.
Other questions?
Thanks for the talk. I'm curious, as you move to more general scenes, do you have the intuition that more complex primitives or a program primitives will be necessary to describe like a field of flowers as compared to a building?
That's very interesting. Okay, so I have two answers to this, which let me first find my mouse. Where is it? So one is, if I go back to this, one is something that we didn't talk about. It's a paper that was never happened. It's frustrating. That is, if you're going back to going to the real world, that's for flowers, or even just for this table, right? So if you look at the lag, where the lag is a cuboid. Is it really a cuboid, or it's not really a cuboid, because at the bottom of the lag, right, there's kind of tiny decorations here. So these kind of details are all lost. So is that possible? So if you assume the primitives of people the same as rectangles, they're not rich enough. So one pretty straightforward idea is, can these primitives also be learned by parameterized by neural networks? Especially these days, in computer vision, all this intensity representation are very popular, right? Everything is like SDF and NERF and stuff like that. So if you can parameterize those primitives and learn neural networks, that at least make your expressiveness much better. And going back to flower, that is a bit more different because there it's not like a primitive, right? Because even it is more like you have this recursive structure. So I think it has to, again, goes back to, maybe that goes back to the even earlier example, that is in some sense, these are like flowers, right? So they're grass, and it's sort of like flowers. So how can we capture that, right? So here, maybe the regularity of structure doesn't come from the fact that it doesn't come from the fact that the chair has 4 legs that kind of has this regular layout. It comes from the fact that these things exist in the first place; they're all the same. And yeah, there are these things you probably want to parameterize and use the same plane. But let's say each of these is flower. How you parameterize it? How much 3D you need is, I think, a lot of exploration needed.
Great talk. I have a kind of a philosophical question. I'll make it grounded in a moment. But I don't know if you know the history of modeling the orbits of planets in the solar system. But for the longest time, we thought everything rotated around the Earth, including the sun. And then Copernicus and others decided that maybe we all rotate around the sun, which is a very simple model. But yet the early versions of that model ended up being much less accurate than the models of motion, where everything rotated around the Earth, because they got these tweaks and hyperparameters that predicted the movements. But the first models of heliocentric orbit were actually less accurate, even though they're simple. So there's this philosophical question: how can we actually define what is simple? And then I'm going to make this more grounded in one of your examples on this, perhaps a more trivial example, which is you have this example of a corridor, and the prior of simplicity is symmetry. And you assume basically, and this is a reasonable assumption, that the camera was perfectly aligned to the center of the corridor. If the camera was a little bit off center, there is a symmetry there, yet someone has to know that you have to shift the camera view in order to identify the symmetry. Do you have any comments on this general?
Well, okay. I think I have a 2-part response to that. The first minor point is the camera doesn't have to be perfectly aligned because we estimate the vanishing point. So everything surface novel computed based on the vanishing point. Just like in this building example, it's not like I'm seeing perfectly centered toward the building. So that is okay. But I do agree with you on this more fundamental question, because essentially we go back to the question that is, I think it's more like what is the sun model has to be more accurate than the Earth model, but it's harder to have more parameterizations. So in the first place, it didn't appear to be as accurate as possible. So now that the question is, there are 2 questions again. One is how to search for the right parameterizations and getting the right parameters. And the second is, can we design a better, I would say, likelihood function, or what is the space you should compute a likelihood so that it becomes not as sensitive? It makes optimization problem easier. Because we have all this, if you think about, sorry, Vikash is going to present in a few hours, so I'm not going to, his work is great, but for all those probabilistic programs, because you're thinking about the building example, so I was thinking about what he presented last night, right? So for all these generative models for vision, and 20 years ago, people say vision is inverse graphics, DDM, CMC, and those kind of things. That doesn't work as well. Why? Because the latent space is hard dimensional, inference is hard, but also they want to reconstruct everything in the pixel space. Pixel space is so noisy. And every pixel, again, think about the problem intrinsic image, right? Pixel space is actually the same ways, different parts of ways. One part of it can be completely orange or red, the other part can be completely white, just because there's light, right? So it's very sensitive, and doing everything in the pixel space make optimization problem so much harder. In some sense, that's also why this paper just right after this, they were like, okay, maybe this feature is a bit more robust. So if let's say the Earth model and the sun model, the sun model is more accurate, but harder to search parameter, but also partially because you're computing everything on the trajectories. If there is some kind of hierarchical, feature space that you can, in some sense you have your curriculum, but you start with a more abstract space, or maybe like a program structure space, then maybe you're maybe your likelihood function optimization landscape will be a bit smoother. So maybe it's easier for you to search for the right parameters in the space where you have more parameters like the sum model. Maybe that's an idea. Granted, in computer vision is that you don't have to do everything in pixels, right? There's all those high-level abstract vectorized images, or there are things like surface normals, or intrinsic images, or contours, or the notion of parts and objects and object positions, right? Different part of system identification you can do in robotics, and these can also be different levels of feature space that you can do your search and optimization in.
This is really cool. Thanks. Could you say more about the visual question answer? Like what the language was you were using and how you translate from natural language to it?
Oh, you mean the DSLs for the semantic programs? And it's very simple. That's actually an assumption, right? Because for all these things, essentially you have to assume DSL unless you do things like Dreamcoder. But even with Dreamcoder, you have to assume a very basic set of DSLs. So when you're parsing those questions into semantic programs, then people will say if the DSL is very complex, then you have a lot of structure bias. But it turned out we don't have that much. We only have a few things. In some sense, I feel like that's very related to human cognition, like what humans know, what babies know when they're 3 months old. In the sense that there's notion of objects, and objects have attributes. So that's what we mean by future. So we call it future. And then there's the notion of 3D space, and objects can be in front of or behind each other. So this is something we call relate, which is basically unary and binary predicates. And then there's something we call counts. That is the notion of numbers. So what does it mean by 0? What does it mean by 1, 2, or 3? And almost that is it. So because exist is basically, if there exists something means if there's count something, that's 0 or not, right? So basically we just need very few predicates, which is future, relate, counts. And maybe there's one more, I can't remember, but mostly that's it.
Those you like write them by hand from the natural language description to get away
Sorry, say it again.
How do you get from the natural language descriptions of questions to those programs?
Well, you do the thing I talk about here, right? So you search to get these kind of different definitions, and you try to identify which ones are.
All right. Oh, one more question back.
Thank you for the excellent talk. This may be kind of a predictable question, but we have now, these really amazing representations, where you're able, from text, from a few images, to sort of largely reconstruct and then render from viewpoints, a variety of very sophisticated images. And when you have large data sets of these, you're often able to infer fairly strong priors over what objects look like, what kind of symmetries things have. And in many cases, the symmetries which may exist are so complicated to express, like certain things have radial symmetry, certain things have symmetry only like the stalk of a flower, but maybe imperfect in certain ways. And there does seem to be a point at which the task of expressing the DSL for these things is so sort of complicated and fuzzy that it becomes sort of challenging to do in general. I guess I'm wondering how you imagine sort of this task of constructing sort of ever more complicated DSLs sort of interfacing with the sort of ever increasing ability it seems to sort of do these kinds of implicit learned representations that may make the challenge of sort of reconstructing these very complicated objects simpler.
But thanks. So I have a clarifying question. That is, when you say implicit representation, because you mentioned a few things, and to me they're not exactly the same thing. One is you say larger data sets, and you can go from language. So that sounds like you're talking about DAO-E and party and those kind of things. But then you also talk about, but that's not implicit. And then you say implicit representations that can view synthesis. So that sounds like nerve and stuff. So which of them are you referring to?
So I think very, very recently there's been work on 3D image generation from text, for example, Ben Poole and others that have done this work.
You like Dreamfield?
Yeah, Dreamfield, for example, which to be fair is still not great. But I think there's also been work on, for example, neural representations, implicit representations, like neural voxel fields of various kinds from like one or two views of an image, you know, like the sort of like low data regime of like nerve reconstruction with like very strong bias over the representations.
Well, I have too many things to say about it, but let me start to say a few things. One is, it is not exactly clear to me if the low data regime thing will work really that well, because I think there's some kind of very fundamental challenge there. No, sorry, there are just too many things. So nerve works well because it's dense sampling. It has 100 images, and so it can you do solve a complex optimization problem. You don't even need learning, right? If you look at planoxels, you just do optimization that works so well. So it's more about you have dense sampling, you do small optimization. And what actually shows there is the importance of symbolic representation. That is the notion of 3D space. And you make volume rendering differentiable. In some sense, volume rendering is a differentiable program. It's computer graphics there for 30 years. Nobody really tried to make it differentiable. Of course, it's clearly differentiable. By making it differentiable, putting it with learning, you actually can do nerve. So that is in some sense the notion of inductive bias that you need 3D. And it works well because it has 100 images. It's more like dense sampling. Not clear if it works with one or two. If you look at pixel nerve and those things, it works so much less well. And then there's a question about, you talk about language. Language is interesting, and clearly I think it's definitely true that if you have anything connected to language, you want to have something. For example, if I do anything with language, like in this for now, I want to do a lot of clip embeddings or any kind of GPT-3 embeddings. I don't want to do it from scratch. That makes total sense. But then there's a separate question about how language can be connected to implicit representations of dream fields. I feel like there's two things, right? There's language understanding. There's how you can tie the language to generate 3D aware scenes. That is more like a nerve thing. So there are two different things. And on top of all these, I feel like there's this point which I sort of believe, and I try to convey to Charles yesterday. That is, there's a communication benefit of having symbolic representation, because when humans write code, why do we write code in Python, or why do we write code in natural language, right? If I want to ask you to do a program, why don't I just write? Can I talk to the system and just explain everything in English and the system write? And why do I still need code? Why do you need a Python and functions and stuff like that? I feel like sometimes there's a little bit of communication cost. That is, if I have, if I'm an architect, I'm designing some piece in a building, and I want to deliver something to a different architect, and I want to make changes to it. Sometimes it's much easier. There's lower communication cost if I do this in the program space, especially when both sides are like professionals, than doing everything in natural language. So there is at least a need of, if you think about every AI application in a human-centered way, then there is a need to have this structural representations for communication. So at a very minimum, even if eventually everything engineering can be done magically with pixels and screens with large models, sometimes we may still need this kind of thing.
Thank you for your answer.
All right. Let's thank the speaker again.